I'm Vikas NT, a 2015 ASGM Fellow, and I'm really happy to be here. I'm super passionate about robots. I've been building them since high school, and I really believe we're at the cusp of a robotics revolution that's finally going to get us robots in everyone's homes, cars, and office spaces. In the past, I worked on a lot of robots for humanitarian landmine detection, and also led the very first team that brought the whole notion of cloud computing for social robots. And coincidentally, for all of my work, I've been referring to one textbook that's been written by our upcoming speaker, Professor Steve Eppinger. So Professor Steve Eppinger is the professor of management science at MIT Sloan. He also holds the General Motors Leaders for Global Operations Chair and has a joint appointment in MIT's Engineering Systems Division. He's currently the faculty co-director of the SDM program, and he also served as a deputy dean for MIT Sloan from 2004 to 2009. Professor Eppinger teaches courses in product design and development, engineering project management, and product management. Notably, he's created an interdisciplinary product development course in which graduate students from engineering, management, and industrial design programs collaborate to develop really cool and new products. He also teaches Sloan MBA, EMBA, and executive programs in the areas of product development and complex project management. Professor Eppinger has co-authored the textbook I mentioned before. It's Product Design and Development, and it's currently in its 6th edition, and needless to say, it's used in hundreds of schools and by over thousands of students worldwide. Professor Eppinger is one of the most highly recognized scholars in the areas of product development and technical project management. He's a pioneer in the development of the widely used DSM, or Design Structure Matrix, that most of us are familiar with here. He also co-authored the textbook titled Design Structure Matrix Methods and Applications, and I actually believe it's being sold outside. Professor Eppinger received his bachelor's, master's, and doctorate from MIT and joined the faculty in 1988. He's received many awards and honors, including MIT's Graduate Student Council Teaching Award, the Sloan School's Award for Innovation and Excellence in Management Education, and he possesses way too many Best Paper awards, quite honestly, too numerous to enumerate, but you get the picture. So this is quite a list of achievements. Without much further ado, I'd like to introduce Professor Steve Eppinger.
Okay, good afternoon, everyone. Thank you, Vikas. That's a very generous introduction. Today's talk relates to my research that deals with how do we understand and better develop complex systems. And I'm going to focus on both the understanding part and the develop better part. So the understanding part has to deal with systems architecture, a topic we've taught extensively here at MIT, including in the SDM program. And the development better part has to do with challenges of bringing new technology into programs. And the key challenge I want to deal with is what we might call technical risk. So you bring in a new technology, and that's great because it might improve the performance of the product or system, or it might reduce our cost of engineering, or maybe the cost of production, or something like that. So there's a benefit, sure, only if it works. And the technical risk is, well, it might not work. We might get halfway through and find this isn't going to do what we thought, and we have a problem with that. And the problem might be, well, now it's going to cost more because we've got to sort of shift to the backup plan, which we didn't like, and that's why we had the new technology in mind. Or maybe it'll just delay our development because it'll just take us longer to get to where we ought to be. And there are various other types of technology risks that come up, essentially because the technology doesn't hold up to what we expected or needed or planned or wanted in the project. And so that's kind of the theme here, is how do we deal with that risk? So what I'm going to talk about today, the way I'll do this is first is talk about, well, why are we always putting new technologies into products and systems? Well, it's because it improves things. So how does that happen? So a little bit of, we'll just kind of return to this, so the S-curve theory of technology improves over time. And then we'll look at, well, how do we plan for that? How do we decide when is the right point on that S-curve, or when is the right point in time to bring technology into our plans, into our project plans? And then finally, how? How do we do that? How do we plan for that, and how do we account for that? And there's a method, which many of you know, called Technology Readiness Levels, TRLs, that you'll see that I'm building on here. So Technology Readiness Levels is essentially the most common way that we think about when is the right time to put technologies in. And it's a metric that we can use during the project. Is it on track? So there's a certain point at which the technology should be at certain performance. And if it's not, we can tell because we have a metric for that. So that seems like a pretty good idea. And what we've found in our research here is that it doesn't always work. There are a lot of problems with implementation of technology readiness levels. And we've done some work on what are some of those problems and which ones do we think we can fix. And I'll show you a little bit about how we're approaching the solution to that. And then toward the end of this talk, I've got a sort of an exercise for us to work on, sort of like a quiz. And that is, I'll illustrate how these factors of architecture and technology risk come together with an example that we can kind of work through. And we'll see if that works today. OK, so that's where we're going today. And let me just start with pushing the limits of technology. So in every industry that's probably important today, we're pushing new technology into products and services and systems. So whether it's automotive with the latest battery, motor, and driving technologies with Tesla and many, I mean, all the leaders in the auto industry, they're putting new technology into vehicles pretty much as fast as they can. With some exceptions with customer acceptance side of things. Oil and gas industry, in order to find the fossil fuels that we unfortunately still need to run the planet, they have to go to deeper and deeper water and colder climates in order to, I guess I would say, in order to still extract the easy hydrocarbons. There are harder ways to get it that's even harder than that. And so that requires new technology in order to do that effectively. Power generation, how do we generate power, whether it's from oil and gas or from nuclear or even from solar and wind, but how do we generate power and have it be able to work very, very efficiently? We're putting new technology into everything from blades to controls to even hydrogen systems. NASA has forever been a leader in pushing the limits of technology. In fact, developed some of the methods we're going to talk about today. Technology readiness levels was essentially a method invented at NASA and now used very, very widely. So they've kind of pioneered in the methods by which we think about technology evolution. And then finally, the electronics industry, how do we make our mobile devices smaller and smaller and yet greater capability every year? And so as you know, new technologies are going to there. So in pretty much every leading, in every technology-based industry, but I actually think in all the important industries today, we're putting new technologies in. So how do we think about what's the right timing and why is this ever increasing? So the general theory of this that I'm sure you're all familiar with is called the SCurve Theory. And I call it a theory because it's not exactly quite true, but it's a nice idea. So it's a pretty useful idea that technology improves over time. So this is performance. Technology gets better over time. Although you see the horizontal axis here, it's not exactly time, because it doesn't really get better all on its own. It's effort. It's how much effort we put into it, how much work we do, how much money we spend, how many people are working on it. And so it's effort over time. And then the second thing you see on here is, well, the shape of these. So it doesn't just get better over time and keep going. It levels out. And the general idea, theory, by which it levels out is we reach some fundamental, maybe physical limit. There's a reason why it can't work better, and we can't break the laws of physics. Unless we have some new concept or approach or new technology that has a different fundamental limit, and that brings us to the last point, is that you could have multiple curves here. And of course, the red curve has a higher fundamental limit. And then finally, the issue is, well, where are you on these curves? And where do they cross? So if we're here at this point in time, well, it's not hard to know how well this technology works and the other one works, because you could assess them, measure them right now. But you really don't know the future, right? So you could draw the red curve so it tops out below the blue one, right? Because you don't really know. Unless you could assess and have an idea, what is that fundamental limit? And often we don't know that, but sometimes we do. All right, so that's the theory of S-curves, the basic idea. And this has actually been shown to be roughly true for a lot of kinds of technologies. And when I say roughly true, I mean they do improve over time, and they do have limitations, and they do get taken over by some future next generation better technology. For example, This is in the automobile industry related to the tires, the fibers inside rubber tires. And years ago, cotton was used as the fiber in tires. And it didn't improve very much because cotton as a natural fiber, there's only so much you can do with a natural fiber in order to kind of modify its properties. But synthetics, of course, there's lots of possibilities. And so all the different synthetics over the years have improved. And you can kind of see S-curves and one curve taking over when the previous one topped out. And so this is a bit of credibility or evidence that perhaps that theory is roughly right. And finally, if we were to look at a lot of different technologies, so here's and this is from some of my MIT colleagues who looked at many, many technologies, how quickly do these things change over time? And so, for example, and we'll just start in the top left, I'm not going to talk about all these, this is Moore's Law. This is computing technology and how it improves over time. And as you know, Moore's Law for about 50 years has sort of held. That is, and maybe it'll top out, but we're probably still on the upside of that. And it's held at a certain rate. But yet other technologies have actually sort of held, but at different rates. So the rate at which technologies are improving are quite different. And if you look at all of these, actually the faster ones are more digital technologies that are kind of all driven from Moore's Law in some way. So medical imaging, for example, that's improved a lot over time in terms of performance, largely due to computing has improved a lot over time, largely due to transistors and Moore's Law and so forth. And so these things are not unrelated rates of improvement. OK, so let's say we want to put some new technology into our new product or system. When is it time? So how do we think about planning that and getting that into the right place, project, at the right time? OK, so NASA, which has been kind of a leader in thinking about this, they've got, well, I guess I would say it this way, they have such a budget that they can put in any technology they want. It's just a matter of time and money. And they can plan the time and they can spend the money. And so they have actually more options than most in terms of what technology to put in. It turns out they also have, rather than kind of a big customer pull and a lot of competitors, they also have a lot of control over what we're going to develop, right? If they don't think it's feasible to, a manned mission to Mars, then we're not doing it. And so they actually have more degrees of freedom than most businesses, let's just say commercial, competitive businesses have in terms of technology planning. And they have a method for this, which is called road mapping. And roadmaps are pretty common in a lot of industries. There are lots of types of roadmaps. This is what we call a technology roadmap. That is, it particularly maps out, it plans what technologies to put into our projects over time. And as complex as this is only one of 14 of their technology roadmaps. This is just the one for launch propulsion systems, and there are 13 more. But it also combines what they do in their different directorates. So like the red stars are SMD, that's Space Mission Directorate. And then, Science Mission Directorate. And then SO is Space Operations Mission Directorate. So for the different missions they do, and there are many, many different small and large missions and types, they're actually deciding which technologies for which subsystems, which technology do we want to put in. So that's actually a pretty useful idea because it can actually plan out for many, many years in the future. Now, to bring this down to earth, so to speak, and to make it simpler, here's an example from a commercial entity, from Xerox. So Xerox, over time, would plan what technologies for which subsystems of their products do we want to count on, do we want to put in. So, and over time, these are sort of different product generations, new system development, new platform development, and so forth. Over time, we'll count on or expect to and build in different technologies. And so just to think about any one decision, for example, when do we move from the keypad user interface to the touchscreen interface? Or when is it time to put in the touchscreen with remote interface, right? So that's any one of these technology transitions is actually a big deal decision, right? Because we're going to put that plan to and build that technology into our product plans, or we're not, or we delay for the next generation. So the method for doing that, so now I'm trying to drill down on the method for doing that. What's a good method for doing that, and how do we plan for it, and count on it, and manage the technology risk? Okay, so, well, just as we have a product development process, we also could have a technology development process. And so you could say, well, the method for that is put it through the TD, technology development process, such that it exits at the right time that you need it for the PD, product development process. And that would be its transition. And then that transition point would be, the point where you need it for that next product line, right? And so that's kind of the basic idea, right? So you have maybe two different processes. Now, not every business separates technology development from product development, but it's becoming a good thing to do, I should say, it's becoming a more popular thing to do today, is to reduce product development risk by putting robust, ready-to-go, proven technologies into the products, as opposed to fine-tuning those technologies for the first time ever as part of the product development process. And that's fraught with risk and difficulty. So if we were to separate it, the idea is we put into technology development well in advance what's on our future product development, product technology roadmaps, the maps I just showed you. Right? And then the question is, well, when is it really ready? When is it ready to transfer? What are the requirements that we need, which would be how we would measure if it's ready? And then, is it going to be ready on time? When is it ready? And so readiness or maturity are the terms that are used for, essentially, we've tested and we're sure that it's going to work and we can count on it with minimal technology risk. And if it's immature or not quite ready, then there's a chance that the downstream project will fail, and it'll iterate, and it will cost a lot more. And the iron triangle we talk about in all those ways in which things can go wrong. Okay, so that's what we want to kind of deal with. So how do we think about, is it ready? So now the method that's now become pretty widely used, called Technology Readiness Levels, or TRLs. So now this has been around for 30 years. So, I'm sorry, 40 years. So for 40 years. So in the early 70s at NASA, they started to use this method of assessing the technologies. Now, I'll explain this just a little bit, but I'm guessing half of you use this in some way. So let's just do a quick show of hands. How many of you have used TRLs in your professional practice? Not here as a student, but actual, real professional practice. Okay, maybe I have a third of you. So for the other half, maybe you're somewhat familiar with this, but I'll explain just how this works. And it's great that a third of you have actual practice in doing this, so we'll get some of your thoughts on it later. Okay, so the idea is on a 1 to 9 scale, we'll rate or assess how ready, how complete, how mature is the technology for a certain purpose, for our intended application. So it's no good to say, well, this is ready if you want to use it for that, but I want to use it for something else. That doesn't work. Is it ready for our purpose? Okay, so you have to have a purpose in mind, a product or a mission or a system or something like that. And so on this, in the 1 to 9 scale actually has definitions. And so at level 1, it's, we've got, a couple of equations that represent how the sort of the basic working principle, and we've observed that maybe in the lab or got some evidence that this equation or model is roughly right. That's not ready. That's level 1. And then, by the time we get to level 2, 3, 4, we've actually got a little bit of a prototype, maybe a breadboard. I mean, it's not ever been tried for real out in the field, but we've got some working model of it. By the time we get to level, say, 6, we actually have a model at the subsystem level, and it's actually been demonstrated in what we call a relevant environment. So not necessarily the field environment, but a simulated environment or a test environment. So that's getting pretty close. And by the time we get to level 7, it's actually worked. So level 7, and these are NASA's definitions. Other industries have slightly different. So they talk about space environment or whatever the target environment might be. And so in other industries, they would say a system prototype demonstration for level 7 in operational environment. So it's in the real world environment. But it's still a prototype. And, but you can see that's pretty much where you would be in the PD process. So if we're going to enter it into the product development process, it's of course going to enter well before 7, but probably not at 1 or 2, right? And so one of the key questions is, at what level do we count on it? Do we have confidence that it's going to work in the product? And of course, and by the time we get to level 9, that's something that's been proven, it works, we have experience with it, and you can pretty much use it in other environments just like that, in other new products or systems, without a whole lot of worry about it. So these are the 9 level TRL definitions. Now, so these are NASA's definitions, which they've been fine-tuning over the years. Other industries have adapted them. That is, they've used them, they've adopted them, but they've also translated them into their own language. And so a lot of businesses, companies that I've worked with, some of your companies here that have been part of our fieldwork, have your own slightly different definitions, but they're essentially following these levels. I don't think I've ever found any company that's implemented them where they have totally different definitions. So your TRL 7, if you're using a 9-point scale, is pretty similar to NASA's TRL 7, is what I've observed. Some companies use a 7-point scale, which is a different story, but almost everybody seems to use this 9-point scale, just modified the words for non-space systems, essentially. There's also some evidence that this helps. So let me describe how this is used, largely in space and US defense, and some evidence that it's a good idea, okay? So first of all, this is how we align the readiness levels with the development process. So remember I said that you probably wouldn't enter the product or system development process with something that's at TRL level 1 or 2, or even 3 or 4. That is, until you're really pretty sure it's going to work, you don't want to count on it. And so the idea, and this is using the defense acquisition process, and the reason I use this is because all the companies I've worked with, and I've seen this type chart from them, they don't release them publicly. But honestly, they don't do something terribly different from this anyway. Nevertheless, this is a public kind of version of it. All right, so the defense acquisition process is this one at the top. And essentially, this is what they call systems acquisition. That's really where the product system development process is. And so point B, triangle at the top with point B is entering the product or systems development process. And before that, between A and B is what says technology development. So that's the technology development process that should be proving out the technology. Okay? And now the TRL transition, you see we're at TRLs 1, 2, 3, which is kind of science or early research. And TRL 5, 6, that's happening, that robustness, that proving it is in the technology development process. And then 7 and beyond is in the product or systems development process. And so it appears that the transition point is this 6, 7, right? And that kind of makes sense. If you look at the definitions, you'd say, well, by 6, we've got a model demonstration in a relevant environment. We ought to have some confidence that if it works there, we ought to be able to work out the bugs and do the robustness and proving out that it'll work as we develop the real thing. It'd be hard to get much beyond that until you've got the real thing developed, right? And so that seems like that's about as far as you might be able to go before you enter the system or product development process, right? And so that's what we call alignment. So we've aligned these stages, the requirements, to the product or system development process. So alignment is a key issue. And that question of how do they line up is one of the important questions in planning or factors in planning these processes. Okay, so the Defense Department, actually the Government Accounting Office, GAO, which monitors a lot of things in the US government, including DoD, did a study of systems acquisition projects, buying missiles and tanks and other kinds of defense systems. And they actually did a study that asked, at the beginning of system development, which was that point B, at the beginning of system development, were all the technologies that we used and built into the project, to the system, were they all mature, or were there some of them that were less than TRL 7? Okay? Now I said 7 instead of 6, so let me just explain that. It's actually the requirement is 6. The expectation is 6. GAO being, I don't know if there's anybody here from GAO, let's just say conservative accountants, for lack of a derogatory term. They're pretty conservative, right? So they said, we'd love them to be at 7. Let's just see what happens for 7 above. So it'd be nice if this study were done 6 and above. OK, so they said, if at start of system development, you have all mature technologies, that is TRL 7 and up, how do the projects go? And compare that to if you're at the start of system development and you have some, 1 or more, technologies that are immature, that is 7 or, below 7, 6 or below. And the difference is huge. So development costs, that's how much we pay upfront for stuff like engineering and prototypes. Development costs, essentially on budget, 2.6% over budget. That's pretty darn close. To 32% over. So huge impact on development cost if you have some technologies that were less mature. Acquisition costs, essentially on target, that this is what you pay for buying them after they've been developed, right? So future contracts. Acquisition costs, essentially on budget, as expected, which is pretty remarkable, to 30% over cost. And then schedule delay, essentially on time to 20 months delay. So the impact of essentially using immature technology and counting on it in projects is huge. That's what this evidence shows. OK, so that's, I think, one of the strong reasons why TRLs have become so popular. They seem to really help you assess, are you putting the right technologies in at the right time? And are they really ready to count on? Or should you, use alternative technologies that are more mature? OK, so given that, we've been working with a number of different companies, some of your companies here, some others in our study. We did an empirical study that asked, well, how exactly are you using TRLs? And do they kind of hold up to the promise? Do they work in terms of technology planning and so forth? And these are just some things that some of the engineers, systems engineers that we talked to had said. So for one thing, if 3 of us were working on a project together, would we all assess the component at the same TRL? And so the sense is that it's a little bit up to fuzzy interpretation. And in particular, from the Deere quote, inevitably the person who favors the technology will interpret it higher, which is often the person who's, favors it. Might be because it's their responsibility, or it might be because they're a customer of it. And they say, oh, yeah, it's ready to go, and incurring all that risk and so forth. Even from NASA, which has 40 years experience doing this, internally we've done several studies that point to the ambiguities and improvements needed in the Technology Readiness Assessment process. And so they agree with a lot of our findings that it works, but there's a lot of improvements, and we'll talk about those next. And Google, which is actually relatively new company, of course, but relatively new to using technology readiness levels. So we worked with some of the folks in Google X, which is kind of their hardware side. Think glass, driving cars, all that kind of stuff. Right now, our technology development process is pretty haphazard. Maybe no surprise with Google, but we say, OK, that looks great. Do you think it'll be ready? So that's kind of, they were interested in, are there better ways to do that assessment? TRLs, obviously. So I'll just say a little bit more about our empirical study. When I say that, it was essentially a set of interviews done by Allison, who's sitting over here, a doctoral student here at MIT, with these and a lot of other companies, and talked to engineers and system engineering managers about what are some of the challenges in using this, how does it work, and how does it fail, and so forth. And I'll just show you some of the results of that study. So one of the key results is, there are a lot of challenges in using them. It ain't perfect, okay? There are a lot of ways in which it's a little bit fuzzy or it can be improved. So for example, and in fact, we identified 15 specific challenges. And you could think of this as, if it's going to get better over the next 10, 20, 30 years, what do we got to fix, okay? And I actually believe most of these are fixable challenges. And in fact, in some of these challenges, I think some businesses, some companies, some implementers have actually found pretty good ways to do it, but nobody else knows about it. So in our studies, we actually found pretty wide variance in practices. So I think fixing some of these challenges is partly a matter of sharing best practices. And so we grouped these challenges. There's a whole bunch of issues related to system complexity. And I would summarize it as in this way. We rate TRLs essentially for component technologies. So is this component, which is using this new working principle or technology, is that ready? Is it mature? Have we used it before? Or is it new, right? as opposed to how is the whole system working. And as you know, sometimes you have a component that might work, but doesn't work in the system with the other components. So those we think of as system architecture, complex system challenges of the type that we've focused a whole lot here in this program here at MIT. So I think there are a lot related to that, and I'm going to illustrate one of those in a few minutes for you. And then the second relates to how do we manage the whole project. For example, if things don't go right, what do we do about it? So that's kind of project management issues. And how do we kind of plan for these over time? And what's the right timing to put them in? Alignment of the process, as we discussed earlier. And then others are just, I think, purely about, it's just hard to rate these things. You and I might rate them differently. Maybe we could use more precise definitions and scales and so forth. So this was actually, I thought, a pretty useful finding. What it says is that after 40 years of using TRLs, this is not even a mature method. Maybe it's at TRL 3 or 4 or something like that. So there's still improvement. There's possibly research to do, practices to share, and I actually think some new methods to be developed. And actually, our research agenda is to help, not necessarily to fix all 15 of these, even though I believe that's possible. We've actually picked off some of the harder ones, not some of the easier ones, because I think some of the easy ones, well, anyway. So before I tell you a little bit about one of the things we're doing, we did a little empirical validation of this. We actually sent a survey to INCOSE members with Pat Hale's help as former president of INCOSE. And we sent it out to hundreds of members of INCOSE around the world and actually have some validation that these are important things. But we also found out which ones are more important based on their practice. And here's what that result shows. So these are the 15 challenges I list on the left with kind of shorthand titles. And this is the criticality based on the survey, so the empirical results. There's a pretty interesting type of survey that we did, which I won't describe. But I should just point out that the top 4 challenges all related to this issue of system integration. So I want to focus on that one. They all relate to the issue of system integration, which is primarily about a component TRL doesn't mean the whole system's going to work, even if the component's mature. So think about it this way. You have a mature component technology. So like in NASA's terms, maybe we have some coding for the shell, the exterior of a space vehicle. And we know it's worked in some, maybe in re-entry to Earth. Well, how do we know it's going to work for entry into Mars atmosphere? Right? So it works, and it's mature, and it's like TRL 9 for the next Earth mission. But for the next Mars mission, what TRL is it at? So those are examples of things that, you take mature technology, put it in a new system, and it's no longer a TRL 9. Or we integrate things. So those are the types of issues that turned out to be the most critical. And so I actually think we could fix that. And some of the thinking that's grown up here at MIT, I think, can help to fix it. So that's the last thing I want to do today is explain that. Vikas, when he introduced me, mentioned something about this DSM method. So does anybody remember that stuff? So half of you here were students in my class at some point and so forth. OK, so I'm going to just use this to kind of illustrate the idea of thinking about a system using TRL. So now this is, I'll explain what it means in a moment. But where this came from. So this came from some work at NASA done by Tim Brady, who's one of our SDM alums. And back to NASA, he said, this matrix stuff I learned at MIT could be really useful. And I wonder if we can blend that with the TRLs that NASA knows and loves so much and have it help us understand not component technology risk or readiness, but system level risk or readiness. Solid idea. Great idea. Let me show you what he did. I don't think it's quite perfect, but I think it's a really, really good idea. And then we're going to build on that. So here's what he did. He said, all right, I'll take a mission, say Mars Pathfinder, which is one of the Mars missions which did not crash on Mars. Let's just say this is one that worked. OK, so a Mars mission, the Pathfinder. And then we'll create a DSM that is a model of the components and subsystems and how they're connected. That's what the DSM is in shorthand for those who haven't seen it before. And then we'll add to that the TRL in the following way. The way he added the TRL, so is this extra column here. This first column that's colored, this column here, it says TRL. So this isn't exactly the TRL, which is that 1 to 9 scale. It's more, he actually called it technology risk level. So we mapped the 1 to 9 TRL into, I think, a 1 to 5 risk inverted. What that means is a big number here means it's a really new, high risky thing. Okay? And so this risk level 4, you see that it was the arrow shell. I don't know if you see that, like fourth one down, arrow shell, heat shield, TRL 4. That's the pink one there. And others had TRL 2 or 3 or 1. So the ones are things that were sort of at TRL 9, that is, they were precedented, work in the environment, and so on. And then others were at lower TRLs, which give this higher risk. And then he computed a value in the matrix based on the criticality of the interface, which is what all the shaded cells are. The criticality of the interface times the TRL for both the row and the column, meaning the two components that are interfacing. Okay? And what it showed is that, well, there's whole areas of technology risk related not just to a new component, but a new component connected to another new component. And as the interface itself was never proven already. And even if you have a mature component interfacing with a new component, there ought to be some risk at that interface. And so that's the idea behind this. So I actually think that's the kernel of a really strong and useful idea. I think we can improve on that. So we're working on maybe better ways to think about system readiness. I think there's some problems with the way this kind of scale and kind of assessments are done. And I think that can be worked out a little further. That's one of the things that we're sort of working on. But now, just to kind of illustrate this with for you, so that you can take something home to think about and something that you can use, I'd like to actually have you think about a simpler form of this in the following way. So here's an exercise. So I want you to think about how would you do this. And so I've taken a portion of that Pathfinder matrix, just a portion that's this 15 components. Okay? And then I put onto the diagonal is the TRL for each component. Okay? So this is TRL 8. That means, you know, almost been used reliably in systems. Okay? TRL 8 is for this land or pyro switching. Okay? And so forth. And so you see TRLs from 5, 6, 8, and 9. So 4 different, right? So 9 is mature, 5 is not quite ready for prime time. Okay? And you also see that I've grouped the components into 3 different systems. There's the cruise and launch subsystem. There's the entry, descent, and landing subsystem. And there's the power distribution subsystem. So these are the components in power distribution. These marks relate to their interfaces. If you remember how to read DSM, these are interfaces. That says this component interfaces with that component. The solar array interfaces with the lander shunt limiter. That's what that interface means. Okay? Okay, so now the question I have for you is the following. How would you think about the readiness, not of the components, but of the subsystems, and then of the system as a whole? Okay, so we got 3 subsystems here, cruise and launch, and it's got 3 components that are at TRL 9. We got entry, descent, and landing. It has 5 components at various TRLs, and we have power distribution. It has these other 7 components. Okay, so you could rate maybe on the 1 to 9 scale. What is the readiness of each subsystem? And you got to think about what would that be. And secondly, what would be the TRL for the whole system? What would be the readiness, you might call it system readiness level? What would be the SRL? What would be the readiness of the whole system, the 3 subsystems together as a group? And before you answer, which I know you got a good answer, before you answer, I actually want everyone to answer. So the way I want everyone to answer is we've got a little survey for you. So if you have a mobile device, half of you are holding it in your hand right now. If you have a mobile device, yes, you too. You could do this on the web page, or I mean, you can do it on your laptop browser or on your mobile phone. Go to that, and it's a survey that asks you to put in a number for the system readiness for each subsystem, and then a number for the system readiness for the whole system. 4 numbers, 4 responses, all in one quick little survey. And you can do that. We'll see the crowd's responses, and then we'll talk about it. So take a minute. Qualtrics can handle 350 at once, so then we're pretty sure of that. Is that all working? Getting results real time. Okay, I'm going to click over to show you the results in the moment. Anybody having trouble with the survey? It's all working? You know what the question is? All right. Okay. Anybody still working on that? No, I think we're ready to go. 2 or 3, but I'm going to move along anyway. Okay, so here's, it's not Safari. There it is. Okay, let me just refresh this. And we should get results, right? There it is. OK, that worked. Thank you. OK, so, so let's look at these one at a time. I want to start actually with this. I guess we're going to see the titles. Hold on. Let's scroll this up a little bit. There we go. OK. So let's start with power distribution. So this one here. So most of you said 8 or 9. OK, so TRL 8 or 9. And well, you got 6 components with TRL 9, 1 component with TRL 8. So why 8 and not 9? You could have averaged this and rounded it up to 9. Who said 8, which is the mode here? Who said 8 and why? So why 8? Can we have microphones now so we can do this? Can I hear responses? I'm going to pick one over here. Leslie, if you come down this side. Yeah, so right over there. So why 8 instead of 9?
Well, there's something about lander pyro switching. I don't know what it is, but there's something there. OK,
so it's one component is at an 8. And so you said, well, the whole subsystem should be 8. So that thinking is called the weakest link, right? It's basically the lowest TRL of the set of components should be the TRL for the subsystem. That makes a lot of sense. That's actually kind of the industry standard. Well, I shouldn't say standard. If any company has a way to do it, that's the way they say to do it. OK? And so I don't know if that's been your kind of company's way you've been told, or if it just makes sense to you. But yeah, so you take the lowest TRL of the components. OK? So 8 and not 9. And some of you said 9 because there are a lot of 9s there. Maybe you averaged it, and you got 8.8 or something like that. And you said, well, maybe. But in fact, the 8 could cause that subsystem not to work. And so there's some sense to the kind of the weakest link theory. OK, let's take a harder one.
To ask a question, I'm curious to know how it could be less than 8.
So why did somebody say, well, I think we're going to get to that, okay. But I don't mind starting with it now. So, well, I'm not sure how we got on that one. All right, so I don't want to embarrass anyone. We'll get to that in a minute. I'm not sure there's a sensible reason for that one. I think there might be some of the other ones, so let's go to that one instead. So how about this, the first one, cruise and launch? So a lot of you said 9 because all 3 are 9. But now I think this is a better way to see the answer. So why did some people say less than 9? So who said, well, let me just go right to this. Who said 5? Or, well, 4. Who said really low? 4. OK. Genevieve, you said 4. Yeah. Genevieve is very experienced systems engineer. There's something to it. So what is it?
For me, it's the interaction with the aeroshell. OK. And we see that, actually, in the matrix. So right here, this subsystem, cruise and launch, has 2 interfaces with the aeroshell, which is at a 5. And so actually, that's why a lot of people might have said 5. Well, not many did. But I think that would justify a 5. Why did you lower it further to a 4? I said a 5. Actually, I'm probably the one person.
OK, you said 5. Somebody else said 4. OK, but let me just say, I'd buy the 5. And the method there is it's the minimum TRL of connected components. And so you looked at the architecture. That's system thinking. So well trained right here. Where'd you go to school? Yeah, so that's system thinking. So the minimum TRL of a connected component. OK? And the rationale for that is, that component, which hasn't been proven, it's not mature, could cause this subsystem to fail, even though this subsystem has all mature components. Because it has an interface. Now, if it had no interface, if these interfaces were not there, you probably wouldn't have discounted it to the 5. And now, by the way, could anybody explain a 4? Why might it even be lower than that? I could imagine an explanation. So this is a yet even more experienced system engineer, perhaps, or someone who's been burned by failed technologies. Let's hear your explanation for that.
You still got integration risk. If I've got a subsystem which is unstable and is interdependent with other elements of the system, I might be having to change those elements of the system. So although they're at 9 in isolation, they're not really at 9 because of the interdependence and the integration risk that arises. You can have a system with everything at 9 and it still doesn't go together.
Yep. So I think that's a great explanation, exactly right. Let me just turn it around a little bit another way, which I think explains it also, is to say that, even that 5 isn't a 5 if it has to work with this 9 and it's never worked together before, right? And so it's to say even I would discount the 5 because it's just never been tested, obviously, in this configuration, or we'd both be at 9, right? And so I think you're nodding your head. That's roughly the same idea. And now, and maybe the harder one is entry, descent, and landing, this subsystem. So the mode is 5, right? Because that's the minimum TRL. And then 4 would be, well, we haven't worked it all together as a system, so I think we've got that explanation. I'm not sure that I could justify the higher ones. I think that's just too optimistic, or maybe you're simply averaging. And the message here is that the architecture matters. You can't just average those. And then finally, what's the readiness level of the complete system? So let's see, the mode here is 5, and so that would be the simple minimum TRL argument. So I got 15 components, the lowest one's a 5. If I were to resurvey you right now, would anybody say 6, 7, 8? No, right? And even 5, there's some argument for, the 5 is pretty optimistic. That's because these components, all of them together, have never worked together, not even at level 5, right? Because level 5, it only tested that component. So I think, this could have been 4. I'm not sure how much lower than 4 I might go. Yeah, it was a matter of making it work on your mobile device. It would have wrapped. It was a little hard. I would have had to tell you all to flip the phone sideways. So, maybe you're right about that. Maybe if I had, you would have given it a 1, possibly so. Okay, so that's a take-home message for you, right? So that the architecture matters related to the technology. I want to just take this one step further with the last, kind of the last part of this thinking. Go back to PowerPoint. So now let's say we're at a gate decision. Okay? So you got that same system, which had one component at TRL 5 and all the others are at 6. And now we're at a gate. So remember this alignment business? It says, you ought to be at TRL 6 by gate B. So let's say we're at point B. We're at gate B. All the components should be at TRL 6. And you got a whole bunch of components at TRL 6, 7, 8, 9. But you got one component at a 5. You remember that? Okay. So what are you going to do? So first of all, what are the options? What could you do? Whitewash. You got to explain whitewash. Microphones, please, Leslie. Yeah. So you're going to fake it or something like that. You're going to say it's not at a 5. It's at a 6. It's right over here. Pink shirt, right here.
You just write a white paper explaining how your previous history with the system justifies a higher rating.
Okay. So that's met with some confusion at least. What else? What are some other options?
Well, in this particular case, you probably say, I can't get that to a TR level 6 without flying it to Mars, so I'm going to go ahead anyway and take the risk.
Well, actually, TRL 6 requires you to do it in some kind of simulated environment. So we could, we can get it to 6.
Mars, but that would be a very expensive proposition.
Well, but that's how they get everything else to 6. But what you're saying is, go ahead anyway, even though we're not at 6, and we have confidence we're going to get there, or we had nothing to lose if we don't get there. I mean, what?
Well, if I really had to fly to Mars to increase my confidence more, I've upped the whole cost of doing the whole thing anyway.
Okay, so this approach that both of you have kind of suggested in various ways is called, at NASA they call it dispensation. We're going to give special permission to this program to move ahead without it. And other companies that we've worked with call it something else. For example, they call it a waiver. The requirement is 6, you're at a 5, we're going to give you a waiver, but you got to write it up. And a lot of managers have to sign on because we're accepting extra risk for that. And so that's one possible approach. We give it a waiver. We move ahead anyway, even though it's not ready. And the reason to move ahead anyway is because it's not just this one component that we're moving ahead. We're moving the whole project ahead. What would the other option be if we don't give it a waiver or dispensation and move ahead anyway? What's another possibility? Hands, or we'll get your microphone. What's another option? There's one over here, to your right, Leslie.
You can co-develop another option with it, have a backup plan you could run with.
So a backup plan, a plan B, an alternative. So what we have is, well, this component's at TRL 5. I got another component that we don't like it as much. Maybe it doesn't perform as well, but it's at TRL 8. So I have a backup plan. And so that, on the other hand, the backup plan might be at TRL 4. Right? You might have had two things. This is the better of the two. So the backup plan isn't always better, but it is an alternative. And so you would want to assess the backup plan. And do we like it? Does it simply cost more or give us less performance, or does it delay the project? Or is it fine and we're ready to go and off we go? Yes, Gloria.
So you can throw more money at it and try to get it ready for up to the next level. So more resources.
Right. So that option is sort of delay the project and focus on that one component, which isn't ready. And by throwing more money at it instead of just coasting along, maybe we can get there as fast as possible because all that attention is focused on it. And so you might want to assess, well, how confident are we that that's going to work? Do we think it's going to work, or does nobody think it's going to work? How much is it going to cost? And then, of course, you could compare that to, well, what's the downside? It's going to delay it by a month or whatever those options are. So I think there are some kind of decision rules and principles. So the way I think of it is there are a lot of options, all right? And so the one you'd like to do is to proceed, right? If this is a go, no-go decision, you'd like to go. Well, we can't because we're not at TRL 6. So what we want to do is something, and there are a lot of options. Well, one option is just cancel the whole project. So we're not going to do this. We'll do something else, okay? And in some scenarios, that's the right thing to do, okay? But in a lot of scenarios, it's not. So we talked about a waiver. So that's the one up there. So we say, well, this isn't quite ready, but we're confident it's going to be ready for certain reasons. And we don't want to delay everybody. We don't want to delay the whole project. We'll let the whole project go ahead, and this one will simply catch up. And maybe by the next gate, it'll be at the right readiness or maturity or testing and so forth. And so that's that one. And then the backup plan we talked about. So we switched to plan B. And that only works if you have a plan B. So one of the principles of technology management is to have a plan B, right? Now, maybe you don't need a plan B on everything, but certainly on every high-risk technology, on the low TRL technology, you should have a plan B. And you should know about that plan B. What does it cost? What are we going to sacrifice? And all that kind of stuff. And then finally, you could delay the whole project. You could say, we're not moving forward until we get to TRL 6, right? And that has other costs. Now, a lot of other people are going to move on to other projects or spin their wheels or waste some resources and so forth. So we'd want to know what is the cost, what is the timing, what are the options around that. And so let me say there's not a single answer to this. There are multiple answers. It's obviously contingent on the situation. And we've just laid out some of the considerations. So let me just wrap up by saying we're working on this. We're working on both the architecture side of it, which related to that first little challenge exercise I gave you, as well as the decision gate side of this. So with that, I'll just wrap up. So we talked a little bit about roadmaps, and that's a key method in technology planning. We talked about technology development being staged and aligned, and the staging and alignment uses a metric called TRLs, which is a really useful thing. We talked about application of TRLs, which has been pretty widespread, but I wouldn't say it's mature just yet, and we're working on this. So thank you very much for your attention today. I hope you can take home something that you learned today.